Hello, this is Ayse Tekes from Kennesaw State University. In this presentation, I will show you the fundamentals and demonstrations of the MATLAB apps we developed specifically for undergraduate level mechanical vibrations, system dynamics and control theory, and vibrations and control laboratories. Considering the three course delivery methods in STEM education, being face-to-face, fully online, or hybrid, and laboratories, unfortunately, the vast majority of the engineering students struggle to acquire a deep understanding of upper-level engineering courses due to the nature of the highly mathematical concepts. And they also struggle to fully comprehend the fundamentals. Traditionally, engineering courses are taught in a deductive way. For instance, engineering faculty comes into the classroom, introduces the topic for about 25 to 35 minutes, and then continues with in-class examples, with just little interaction with the students, mainly in a face-to-face, and this is actually worse in a fully online or a hybrid model. Looking from and these type of delivery methods, students eventually they become passive learners. Looking from engineering faculty's side, teaching engineering courses is also very challenging due to its complex nature. And with diminishing resources available to the engineering faculty, it's really difficult to enhance student learning. Creating in-class engaging activities and implementing those into the curriculum to meet the desired learning outcomes, this requires extra effort and time. However, considering engineering faculty's expectations, for example, junior faculty's research expectations and senior faculty's service expectations, faculty might not find adequate time to create those activities and then implement those into the curriculum. Without doubt, hands-on activities, hands-on laboratories are invaluable. But there are also several factors that make the labs difficult to meet the learning outcomes. Some of the reasons might be listed as the favorably utilized educational laboratory equipment. They are very expensive and they are bulky, which requires these equipment require wide space, so you cannot accommodate many in one space. Students have to wait for their turn. Also, these equipment come with their embedded software. So, for example, mechanical engineering students, they really don't understand a deep understanding of the signal flow. They simply click on the record button to record and also export data. How can we help students improve their understanding of the course material? The best way might be understanding their learning styles, meaning that their preferred way of learning. For deductive learners, they prefer learning the topic from their instructor by taking some notes in the classroom. Active learners, they prefer in-class examples and more engagement. Inductive learners, they prefer looking at the data and then infer the principles behind the shown data. And many of our engineering students are visual learners. They prefer looking at the graphics, simulation results, maybe animations if possible. And I believe that student learning and the way of students prefer learning, they are all tied to each other. It's essential to enable students to focus on the object of learning and discern its critical features. However, these features that are possible to discern often depend on instructional methods. In traditional approaches, students are expected to sit hour after hour in a classroom, being overwhelmed with verbal presentation, and they are expected to absorb the material. When students listen to the instructor lecture, students' role is just passive. They receive information that they cannot process anymore. Students are not really engaged in these kind of delivery methods since they are not given the opportunity to apply what they have been just introduced. If an engineering faculty uses student-centered teaching practices, so students' conceptual learning will be increased in addition to their analytical learning, such that students are introduced to topic and then with an example, they're expected to plug in the data, plug in the variables into the equation to solve the problem. Active learning strategies gives a lot of benefits to the students. It gives them time to process the important pieces of the lecture, and now their brains will be able to work with that information. and there's so much greater chance that important stuff will be stored in their long-term memory. Students greatly benefit if the instructor modified their teaching method based on the needs of the students' learning preferences. Since engineering is the use of scientific principles to solve real-world problems, it's considered extremely important that the theoretical concepts are imparted to the students in a traditional classroom setting, meaning that face-to-face, hybrid, or online. They are supported by practical experiences through the hands-on experiments or virtual laboratories, if possible, in an undergraduate engineering education. Although laboratories are essential in undergraduate education, the challenges for student learning that arose with the COVID-19 crisis and which we're still facing right now made it much more difficult to achieve course learning outcomes that are tied to the laboratories and hands-on experiences. With the COVID-19 crisis, the spring 2020 academic year took an unexpected turn for academics all over the world. Engineering faculty who teaches those laboratories, they had to move online and instruct from home, and they were not prepared for this. This online course preparation takes more time and effort compared to traditionally designed face-to-face and laboratory and online courses. And they were also compounded considering the unprecedented situation where many faculty did not have enough time to go to their laboratories to record the data shared with the students and maybe even recording video of themselves in their laboratories. Even before the pandemic, there was a growing interest in visualizing of fundamental concepts that are taught in a traditional classroom to enhance student learning. If the theory can be demonstrated either using a portable prototype or through visual laboratories, students not only comprehend the fundamentals, but they also link the theory to its application area. In addition, if a 5-minute discussion for critical thinking and reflection questions can be provided to the students, these kind of activities, engaging activities, will profoundly support student learning. Although there are several online laboratories specifically designed for gateway courses such as physics and chemistry, there is still a need for visualizing fundamental topics for upper-level engineering courses. In order to meet the need for visualizing those fundamental topics, we designed MATLAB apps specifically designed for undergraduate level mechanical vibrations, system dynamics and control theory, and vibrations and control laboratories. So one can ask, why MATLAB? Students have free access to MATLAB in many institutions, and an introductory level MATLAB coding class is frequently offered to the freshmen. The program incorporates several toolboxes such as Simulink, Simscape, system identification, symbolic, control design. And our MATLAB apps are consisted of several submodules which are created by using the Simscape toolbox. Another question might arise, why Simscape? MATLAB Simscape is a modeling environment analyzing both rigid and flexible systems using either the blocks provided in the library, or students can just import their CAD model to create 3D visualization of their design systems using Mechanics Explorer. MATLAB app, developed for introductory level mechanical vibrations, control theory, and vibrations and control laboratories, consists of multiple submodules so that students can use to simulate the systems with different sets of parameters. They can analyze their results and simulate the response system behavior with MATLAB Simscape Mechanics Explorer. The MATLAB app can be downloaded to a local computer and simulations can be run offline after. If one is interested in using the MATLAB app, they need to just double-click on the cover page here to have access to the submodules. Students can study 1 mass 1 spring system, 2 mass 2 spring system, then 1 mass 2 spring combinations, then 2 spring 2 degree of freedom system with 3 springs, or 3 degree of freedom system with 3 springs. They can also study a 2 degree of freedom mass pendulum system, and they can design a PID controller to control the position of a single mass or a mass with a pendulum. If one is interested in looking inside the GUI app, they just double click on the little arrow that opens the Simscape blocks. They can understand the inputs, the outputs, and how the system is connected to, or how the blocks are connected to each other. They have access to the Simulink models of each submodules. They can understand which parameters are expected to the command window, so meaning that the workspace, they can see, for example, for the mass pendulum system, they can see which parameters are exported to the command window, again, to the workspace. They can design a PID controller. They can look at the reference data. They can change the reference trajectory. They can look at inside the system. They can add more masses to the system to create a 2 degree of freedom. They can change the reference trajectory. They can look at the output data. Again, they can design a PID controller. And they can also design a trajectory controller for a mass spring pendulum system. When mechanical engineers design a machine or a mechanism, vibrations that are caused either by the external forces or due to the clearances in the joints are undesired, and they need to be reduced or eliminated if possible. Vibration control can be achieved by a passive design or by an active controller with the addition of electronics. One cost-effective solution for a vibratory system, which is subjected to some harmonic motion, is the design of a secondary system, which is comprised of a sliding mass and a spring, as shown in the sketch. Potential learning outcomes of this activity, vibration isolator activity, which can be given as a homework, given as a project or in-class activity or a lab activity, can be listed as design of a single degree of freedom system using MATLAB app, derive the equation of motion of a single degree of freedom system, obtain the system response data from MATLAB app, obtain the natural frequency using the two methods, equation of motion and also the simulated response. Design a vibration isolator for a system having base excitation. Describe how the reduction on the primary mass is affected by the choice of different vibration isolator mass and spring constants, and visualize the force and also force of single degree of freedom and 2 degree of freedom mechanical system. Again, this activity can be given to the students as an in-class activity, as a lab activity, or as a homework assignment. Initially, students are expected to design their own primary system. They need to select mass 1, K1, and also they need to introduce some surface friction to create a realistic system. And this primary mass is subjected to some force, a harmonic force, in the form of A times sine omega t. Here, omega is the forcing frequency, which is equal to the natural frequency of the system. Once students set these parameters in the submodule, the selected submodule, and then they run the simulation, they will see that since the system is forced at its own natural frequency, the primary mass will have excessive oscillations, aggressively moving back and forth. Then, students, after running the simulation, they can plot the response of the system and record the maximum output. As the second part of this, or as the main goal of this activity, they need to design a passive vibration isolator system consisted of a mass and a spring. So they need to select their parameters for the secondary system using the theory. So K1 over M1 from the theory, from their course, they get the equation of motion and they do the calculations and they find this relation. If they can set the equation so that K1 over M1 is equal to K2 over M2, and when system is still subjected to the primary system is subjected to the same external force, they design this new system, selecting the correct submodule and run the simulation with the new parameters. They will see that the primary mass is now damped, significantly damped. After that, they can also plot the response of the system. And here the goal was to reduce the vibrations on the primary mass by 90%, and as seen in this example, they achieve their goal. In order to simulate this vibration isolator activity, students, to design this first single degree of freedom system, they select the corresponding submodule. They double click on it to be able to enter the parameters on the system, and then they select zero free response because we are applying a force instead of giving it an initial displacement. So they select the force response and then select the harmonic force and set the parameters magnitude and the frequency. They design the single degree of freedom system. They get to the equation of motion, and then they apply the input force to simulate the system. Let's complete the vibration isolator assignment in our MATLAB app. If this is the very first time students are opening MATLAB app, the very first thing they need to bring in two workspace data that will allow them to run the simulations with the required data. Here, they double click on the cover page and then select the module that they are interested in working on. They enter the parameters of mass 1, K1, and damping constant. They go to the force response and click on the zero initial displacement since this system is forced. They select the force type and then enter the magnitude and also the frequency, force frequency. Then they run the simulation. Once they run the simulation for their desired simulation time, Mechanics Explorer starts visualizing the system response. Here, they see that the mass is sliding back and forth aggressively. They can go back to the MATLAB command window and plot the response of the system because all the data is exported into the workspace. Then for the vibration isolator design, they now need to select a 2 degree of freedom system with 2 mass, 2 spring. They use the same parameters for the primary mass, but now using the theory K1 over M1 equal to K2 over M2, they need to adjust those parameters to meet the necessary equation. Here they select their secondary system parameters and then enter exactly the same initial force. They run the simulation now with the vibration isolator design, and even by looking at the response of the system from Mechanics Explorer, they observe that the primary mass is damped more than 90%. They can actually see this by just plotting the response of the system. If they initially recorded the initial data, they can plot both primary masses oscillations with and without the vibration isolator together. Let's look at our second example, which is the mode ratios of a 2 degree of freedom system. The learning objectives specifically designed for this example are determining the 2 natural frequencies of a 2 degree of freedom system, visualize the mode shapes of a 2 degree of freedom system, investigate the effect of initial displacement on the free vibration of a 2 degree of freedom system. Use MATLAB app to create single degree of freedom and 2 degree of freedom system. So what's the theory behind this? Consider a 2 degree of freedom system consisted of 2 masses and 3 springs that are only allowed to move along the horizontal axis. And because we're only interested in the calculation of the natural frequencies, a lumped mass matrix model can be just obtained using either Newton's laws of motion or mass matrix method. And from here, students can calculate the 2 natural frequencies of 2 degree of freedom system. Just to point out, our main aim is to visualize the mode shapes of 2 degree of freedom system and also investigate the effect of initial displacement on the free vibration of our 2 degree of freedom system. Because we have 2 degree of freedom system, once students randomly displace the cards, they are expected to see 2 peaks on the power spectrum. Using the theory, if they can set the frequency to, initial displacement ratios to mode 1 ratio, then they will only see 1 peak on the power spectrum. If they set it to the second mode ratio, if they can adjust the initial displacement to make it exactly the second mode ratio, they will see that once they plot the power spectrum, they will see another shifted frequency on the power spectrum. Now let's design a 2 degree of freedom system and look at the mode ratios of our simple 2 degree of freedom system. Assuming that students already broadened the workspace data in the workspace and then double click on the cover page, they select the 2-mass 3-spring system first, and then they double click and then set the parameters. For the simplicity, we make the system symmetrical, so mass 1, mass 2 are same, K1, K3 are also identical springs, just for the simplicity for the mode ratio calculations. Once they design their 2 degree of freedom system with 3 springs, they go to the force response, or just under the free response, they click on the 0 forces because this is now free response. Mode ratio 1 is 1, so they displace the card to the same position in the same direction. Once they run the simulation, on the Mechanics Explorer, they see that the 2 masses, they move at the same frequency. And from here, they can plot the frequency for power spectrum. And even though the system is 2 degree of freedom, they will only see one peak. Now moving back to the second mode, which is -1 for this example, now they displace the card in opposite directions to the same amount. Let's say 2 and -2. One is displayed to 2 cm, the other one is displayed to -2 cm. This time the masses are moving at the same frequency towards each other in opposite directions. They can double click and click on the power spectrum. There's an embedded code in the program, so it plots the power spectrum, so they can actually calculate or see the natural frequencies of the system. Once they randomly displace the card and run the simulation, from the Mechanics Explorer, they see that cards are just moving back and forth, oscillating at their own frequency. They can go back and actually plot the power spectrum. From here, it will allow them to see the 2 peaks now. Our third example is the position control of a pendulum. In this example, to better visualize the effect of a PID controller design, we have 2 pendulums. The one on the top is not without the controller, and the one on the bottom has some PID controller. This PID controller will be can be actually designed by trial and error method, by Ziegler-Nichols method, or students can just tune PID controller coefficients by just using the PID controller block in Simulink. Here, once students select the title PID pendulum and then select the submodule and double click on it, they can select the rod length, the tip load, and also the angle they want to control. From here, they can also select the disturbance. So we are trying to design a PID controller when there are some disturbances acting on the system. They can start tuning the PID controller coefficients and visualize how the system behaves. You know, this system right now, the design controller is not sufficient, so they have to keep tuning the parameters. They can change the P controller, or they can add some integral constant or derivative constant, and then look at the effect of the system response. If they're not satisfied, they can either design a PID controller by just clicking on the tune button, by tuning the PID controller coefficients, which is embedded in the PID controller block. Once this is all set, students can just update the block with the tuned parameters and then run the simulation with these parameters. And look at the simulation response. Here what we're doing is we're applying an impulse force. So someone is just, hitting the pendulum, constantly hitting the pendulum. The number of peaks within a specified time also can be tuned in the simulation, in the configuration blocks. They can also plot the angle of the pendulum. If one is interested in looking at the Simscape model, they can change any parameter. They can change the configuration of the pendulum. They can change the way it looks. They can change the tip load shape as well. We provided our MATLAB app to vibrations, control theory, and vibrations and control theory lab students and collected more than 100 data from those students. Students' comments about their learning from the simulation were nearly universally positive. In particular, several themes were prevalent in the comments. Students appreciated the clarity of the instructions and expectations. They found the necessity to interact with the simulation by manipulating data valuable, and students saw value in visualizing the representation of the system behavior. They commented that the videos are super helpful. What we did, we also created introductory level how to use GUI app instructional videos on YouTube, and they found these YouTube videos really helpful in understanding what they are doing. And they really liked the toolboxes, and they also liked the method. They really liked to visually see the system and all of its components, and they really enjoyed the visuals provided the Simscape models. Introduction of MATLAB app to simulate the behavior of modeling and control of dynamical systems for introductory level mechanical vibrations, system dynamics and control theory, and their associated laboratories shows significant promise as a tool to enhance student learning in these courses. The program is robust in that it can be applied to multiple scenarios, from single degree of freedom to 3 degree of freedom systems. This ability to use the program for multiple concepts provides a significant learning advantage, as students become familiar with the program operation, and they will be able to focus more on how theory applies to mechanical system behavior in vibrations and control applications. Further, student responses to the surveys indicate that they found the learning activities designed to address the key topics of much help or very much help in understanding the theoretical concepts and also in helping them develop their engineering skills. In summary, our MATLAB is open source. Anyone interested in using our app can just download the MATLAB GUI application from the provided link. The MATLAB app demonstrates fundamentals that are taught in the vibrations control theory and their associated laboratories. Faculty, so MATLAB app can be used by the faculty who wants to visualize the topics in within 3 to 5 minutes. They can also interact with the students because students can just download it, but this can be also given as a class homework activity. When students go back home and need to do the homework, they can study on their own pace. What we found really useful, what we really recommend, is if a student is hesitating initially to use MATLAB app because of maybe their MATLAB skills, what we really recommend them to do is complete the 2-hour on-ramp. So they can start with just MATLAB, then continue with MATLAB Simulink and finish MATLAB Simscape. This will only take their 2 hours. After we created the GUI program and provided to the students, we knew that some of the students might have doubts on the accuracy of the GUI app. So how do we know? The GUI app provides us accurate solution. So what we did, we designed a portable laboratory equipment by just 3D printing the main body parts. And we collected free response data from the system. And we were able to find the system parameters using system identification. Knowing system parameters of this vibratory system, such as mass, stiffness, and the damping of the system, we entered the same parameters in our GUI app and ran the simulation. As you see in the video, both the laboratory equipment and the GUI program provides us the same result. So in the future, we are planning to implement or embed more of these videos in our GUI app, so students will have no doubt on the accuracy of the GUI simulation results. Also, future work to extend this pilot effort by investigating student performance through a controlled experimental approach may be of value in demonstrating whether student perceptions of learning are supported with increased performance on homework or exam questions. Further, extension of the MATLAB app capability to address the additional key topics and important system behavior applications will be of value, as the program could be threaded through an online course. The open source nature of the program also can be leveraged to facilitate these future research possibilities with different types of student populations. I would like to express my sincere gratitude to European Control Conference for giving me the opportunity to present our developed MATLAB app. I would like to thank MathWorks and Melda also from MathWorks for funding us and for helping us to implement our MATLAB app to improve the curriculum. I would like to thank my undergraduate student team, design and control team from Kennesaw State University. And thank you very much for joining us today.